Shall we begin?
Yes, sir.
Okay. Okay. So, good morning, all of you. Start. I hope you had a chance to brush up some of the fundamentals uh, of what we discussed the last time. I will just quickly recap and then take it from there. So, what we did the last time was said that most problems in science and engineering happens to be approximating functions, right? Um, yeah. So we cast the problem of function approximation as that when you are given pair of elements which are of the form xi comma yi, where xi comes from the domain of the function and yi comes from the range of the function. The task is to find the underlying function that is there. Okay. We saw some examples also, right? Where the underlying function happens to be simple functions like linear and quadratic functions. So why do we need to do function approximation? That is because uh, one of the major reasons is that function approximation enables prediction, right? So if you know what the relationship between the domain, basically elements of two sets called the domain and range, if you are given a new element in from the domain set, you can predict or estimate what is the corresponding element in the range set. Right? So that is why function approximation is important and necessary. Okay, so the problem was that what if the mapping between the sets cannot be found using like known mathematical tools? Mostly the solution is that you come up with new mathematical tools. So, given this pretext context, probability theory was introduced. So basically, we need that because the relationship between the given sets are rather complex, do not adhere to the existing mathematical framework. Saw some examples of it, right, uh, where the elements of the domain happen to be coming from like R, P, comma Q, uh, where it corresponds to every element in the RP cross Q space corresponds to a picture. Okay. And what you need is the range space comes from one of the two values, like these are called genders. So relationship between the pixel values and the idea of genders cannot be modeled using existing mathematical tools. So that was one example, and we saw some textual example where you have a document and document gets mapped to an abstract idea called emotion, and similarly speech signal to phoneme or words and all that, right? So what's the idea? Range set is not measurable in the sense that they are abstract. Okay, you can't measure emotion, you can't measure gender. You can only give labels associated with it, but the domain can be measured. Okay. As I said, even to solve these problems, historically, people attempted to solve these problems using classical mathematical tools and gave you examples of yeah, speech and images, where speech signal was being modeled from a linear system or nonlinear system perspective, where you have the signal and you model the signal, the output as concatenation of several linear systems or waveguides, and you estimate the parameters of it. Similarly, with image processing, where you wanted to analyze an image, and that analyzing an image was conceived in a hierarchical manner, where you detect edges and you compose objects from edges and uh, primitive shapes, and then you try to make sense of what it is. Okay, but these methods mostly it did not yield human level performance. Okay, because this constructing the functions that would map speech signal to phonemes or pixel values to complex object relations are not trivial. So then came probability theory. I mean, it was actually not that, historically speaking, statistics and probability theory was around, okay. But the application of probability theory as a mathematical tool to solve these kinds of problems was not that popular before, let's say, late 1980s. Okay, the probabilistic tools were not the go-to tools to solve these kinds of problems. But yeah, so people realize that using classical function approximations may not be the best thing to do while you want to solve these kinds of problems. Okay, so with this context, right, we were looking at what probability theory was. So, okay, so maybe I'll pause for a while here. Any questions so far? This is all some historical context. Any questions here? Okay, let's continue. So started introducing probability theory. So what is it basically? It allows uncertainty by construction. Okay. What does that mean? That the functions that we are talking about, which are mappings from the domain and range, can possess quote unquote uncertainties. We want to quantify what uncertainties are. So uncertainties, what does it allow the user to is that it makes function learning feasible. Okay, because we saw that function learning was infeasible in so many cases, and it sort of helps creativity because if there is uncertainty, I give you that example of an artist, right? I mean, if the artist does not know a priori what sort of art is being created, and that's why creative or new stuff gets generated out of it. Okay, we could try to concretize some of these ideas that yeah. Uh, Probability theory starts from this this fundamental concept called a random experiment or a random trial. So, as I said, in the whole of probability theory, this is one thing that has not been mathematically defined, right? I mean, what is a random experiment or a trial? It's just said that it is a process that gives rise to a set of outcomes. That's all. Okay. So anything that gives rise to set of outcomes is called a random experiment or a trial. So collection of all the outcomes of or outcomes are the observations or outputs of a random experiment are enumerated in a discrete set, and that set is called a sample space. Okay, need not be discrete set; it can be a real space as well. Let's not go there. Well, let's just say that the set of all outcomes are enumerated in a set, and that's called a sample space. So examples of random experiment is that you toss a coin and the sample space comprises of head and tail, and you roll an n face die. Then the sample space comprises of n faces of the die. And we also saw some practical examples, right, where taking a picture of a person can be looked into as a random experiment where the sample space happen to be different people, right? Every time you get different people, recording a speech signal happens to be a sample space and so on. Okay, so this was the sample space, and we are not. I mean, it's not enough if we only have sample space, right? Because remember that finally our intent is to map a picture to a gender or these kinds of ideas. For that, what we needed was something called a measure. Okay, it defined a measure. So what is a measure? So given a particular set, take a subset of a set, and for each subset you associate a scalar, right, or a non-negative number such that it has some properties, and the properties are the following: that you take any subset of a given set, the measure has to be non-negative, so non-zero, and if you take the null set, the measure has to be zero, and if you take the measure of union of two sets such that the intersection of them is null, then the measures have to add up. So we also saw an example of a famous measure that all of us know of, which is the Lebesgue measure, which is the length and the area measure in length, area, and volume measure in R1, R2, R3, etc. Similarly, one can define a measure on sample space, right? You have collection of all possible outcomes of a random experiment is what is called as a sample space. Like if F denotes the set of subsets of all possible subsets of omega, then a measure, which is also called the probability measure, is defined on the subset of the sample space. Okay. Probability measure is a measure that is bounded, upper and lower bounded between 0 and 1. Okay. It can be interpreted as the uncertainty associated with a subset of the sample space. The subset of sample space is also called an event. Okay, so probability measure is just like the Lebesgue measure gives you the sense of length, okay, of a subset of a real number. Sorry, I'm sorry. So it gives the notion of a length of a subset of a real of the real the set of reals. Probability measure can be interpreted right as a measure that is giving you the sense of uncertainty associated with certainty or certainty slash uncertainty associated with a particular subset of the sample space. Yeah, this is what I've said. No? Length or areas on R2 is similar to probability on omega. Okay, so this was okay. Now we have the uh, the probability triplet, which is generally called the probability triplet, that is the sample space, the subset, which is the event space, and the probability measure. Okay, this is typically the probability triplet. I mean, again, you can compare this with when every time you define a measure, you get something like this, a triplet like this. In R, no, you have R, you have subsets of R, which are also called the Borel sigma algebra, and you have the length or the Lebesgue measure, right? Similarly, you have a probability triplet, that is omega, and the subsets of omega and probability measure. Okay. Now, okay, there is another problem. I mean, remember that our goal is always to learn that association between the pictures and abstract concepts like gender or whatever. Okay, to do that, we need something more. Okay, there is a measure now. Okay, we can measure. We associated a measure with the outcomes of random experiment, but that's not enough because elements of sample space are not observed in practice. Okay, what do I mean by that? What do I mean by that is that if the random experiment is taken as observing a particular person, okay, and taking a picture, we don't get to see that person, or rather, we don't. Yeah, we don't get to see that person, which are the elements of sample space. But what do we get? What we get to see is an observation, rather some measurement, okay, that we do on the elements of sample space. So this has to be appreciated because otherwise, right? I mean, this notion of random variables will not be appreciated better. Let me repeat what I'm saying. See, while the elements of random experiments are enlisted in a sample space, in practice, we don't get to observe the elements of sample space. Now, why is that? In the example of the pictures that I said, okay, the random experiment is that you pick a person, take a picture, right, and a picture, an abstract object picture, is something which is an element of sample space. You don't get to observe that. What you get to observe is a surrogate to that particular picture. Okay, so now we need to somehow define one other concept. Okay, that would map the elements of sample space to something that we observe so that we can work with them. Is this idea clear? I mean, this is a central idea, right? I mean, because we never go to sample space while we are working in machine learning. We only work on the observations, or rather the instantiations of what are called as random variables. Okay. Why is that? Why is that? Is because when we do a measurement, right, using some sensors or something, what we observe are some surrogates of the elements of sample space, but not the elements of sample space at all. Okay. Now, how do you model that mathematically is the question. We model that using a function. that is mapped from the elements of sample space to RD. Okay, D is an arbitrary number depending upon what sort of application or data that we have. D gets fixed. The example, in the example that we saw, if the sample space happens to be people or pictures of persons, then this function, okay, this function will take every picture or every person and maps it to a real number, okay, in PQ dimensional space. What is this PQ? We envisage this as a picture, a grid of PQ pixels, right? Where every element in P comma Q grid happens to be a real number. So every picture happens to be a real number in PQ dimensional space. So now this function takes a picture, right, or takes a person and maps it to a real number in our PQ dimensional space, and which is what we observe. Okay. Yeah, I will take the questions in a while. Please keep that hand raised, of course, virtually. Otherwise, the hand will start paining. Um, okay. In the second example, the sample space has a head tail. Okay. And the function maps the head tail to, let's say, 0, 1, 2 numbers. Okay, so this is here is a function. The function takes elements of sample space and maps it to some d-dimensional real numbers. Okay, and this function is what is famously called as a random variable. And as I said, it's a misnomer in the sense that it is actually a deterministic function that takes elements of sample space and maps it to some real numbers, or d-dimensional real numbers. Okay. Now, the data that we are given, okay, what is that? They are actually the members or elements from the range space of a random variable. What do I mean by that? When let's say that, we are working with MS data set or some imagined data set, what we get are elements from this RPQ dimensional space, right? We get multiple vectors of dimension RPQ. What are those? They should be conceived or seen as elements, okay, coming from the range space of this function called random variable. Okay, because the uh, elements from the sample space are not observed. Okay, what is happening is you should imagine that, okay, there was a sample space, some random experiment was happening, and there is this function which is called a random variable that has mapped the elements of sample space to the set of real numbers. What I am seeing are the set of these real numbers, which are nothing but the elements from the range space of the random variable, which is a function. And if you imagine that there exists an underlying sample space, which would tell you what was the random experiment that was being conducted. Okay, so this is till this we had seen the last class. So now we will continue from here. Yeah. So any questions here? Please raise your hands. I'll call out names. Let me- Yeah, somebody tell me. This is the one I want. I want a new page. How do I get a new page here?
Sir, you can unselect this, and on the bottom there is a new page button. Page plus page in that column only. Can you open that once again?
Yes.
On the bottom there is a
Yeah,
page.
yeah, got it, got it. So here, text mode. What was the naming convention? This was L2. Okay, so just distinguish some. Where was that thing which we had the sample space, the set of subsets, and a probability measure. Okay, now this show that, yeah, there was this function called the random variable that took elements of sample space, mapped into some d-dimensional real numbers. Okay, this is where we are. Okay, questions. Yeah, Rajagopal.
Hi, sir. Good morning.
One, yeah.
So, sir, I just want to analyze a little bit more on the concept of random variable in the context of our problem of taking a picture and understanding whether it's what gender it is. So,
Hmm.
in that concept, as you said, the picture that we clicked is a member of the right hand side of the random variable definition. That is the
No,
RT set.
Gopal, yeah. See, I encourage you to use mathematically correct terms. Huh?
Okay.
Don't call it the right hand side of random variable. Call it the
Range set.
range space of random variable.
Range.
Yeah,
Range space. All right.
yeah.
So, sir,
So every picture, every piece, every point in data that you get is an element of the range space of random variable.
got it.
Hmm.
Now, I want to imagine a scenario, sir. It's possible, right, that we take multiple pictures of the same person where he is standing in different poses.
Hmm.
So, how does the idea of random variable handle that? Like, so there is one element of sample space that is being mapped to different ranges, different elements in the range set, correct?
No, no, no,
Range
no, no.
space.
See, yeah. A function cannot map one element to multiple elements. No, one to many mapping is not a valid function at all.
Yeah,
Okay. So that does not become a valid function. So it cannot map the picture of one person to multiple real numbers. But why? I mean, that's a good question, right? I mean, that's actually a good question. Let me answer that. See, in that case, the way you should imagine is that the sample space itself has pictures of that person standing in multiple angles. See,
okay.
while I conceived, I mean, in the example that I gave, I understand why that question is question arose, right? In the way I gave you the example of sample spaces, I said that every person corresponds to one object in the sample space, right? It
Yeah,
may not be the case, right? I mean, if you are taking, I mean, that is in the case where you take one picture of a person. If you are taking multiple pictures of a person, then all those pictures becomes elements of the sample space, and random variable will map it to different real numbers for different angles. A function by definition cannot have one-to-many mapping,
got
correct?
it. So we are still not at the place. So sample space has all the possible poses, everything related
Yeah,
to
yeah,
every person on this planet, but
correct,
we're
correct.
still a little away from our final goal where we then analyze the sample space and all the possible poses and find out, okay, these are all actually the same person.
Yeah, see, that way we'll do. See, we are.
Okay, okay.
I've not set up the next problem yet. I'm just telling
Okay,
you what the sample space is and what random variable does. Right
got it. Yeah.
now, that's why I mean, actually, you brought up a nice point. See, I hope that all of you got the question. The question was that in the example that you gave, there was one person, and taking the picture of one person was one element in the sample space. Then if you take multiple pictures of that same person, how do you handle it? Now, the answer to that is that see, you conceive what is there in the sample space, meaning the user would define what the sample space is, because the random experiment is something that is a user defined idea. You see, but what I wanted to tell you is that when you have, like, let's say multiple elements from R, P, Q, or Q, which are images, right, or the set of pixels, you have to imagine that this is the result of this process where there was a sample space and there is a function which is a random variable that has mapped the elements of the sample space to this RD.
Yeah.
Okay, there exists some sample space, some underlying sample space, and you construct that sample space accordingly, right? I mean, it doesn't matter how you construct it. And the good thing is that you don't have to even worry about the sample space once you get the outcomes of, I mean, once you look at the range space of random variables, that's enough. That is why you define the random variable in the first place. Okay.
Okay. So the way I understand this, sir, what you said triggered another thought that
Mhm.
ultimately what we want to understand is the gender, right? Even if the same person repeats again and again, the gender stays the same, so it's irrelevant for the problem. Is that how I
No, no,
should
no.
understand
I
it?
say don't worry about that's what I said. No, don't
Okay.
worry about the gender part yet. Okay.
Okay. Mm-hmm.
Just think about having a few data points,
Yeah.
which are pictures. Now, how do you see those data points is something that we are looking at right now. How do you look at the labels is something that we'll come to in a while. Okay.
Okay.
For now, just imagine that you have a set of data points.
Got it, sir.
Okay. These data points are seen as the elements of the range space of a random variable. And the moment you talk of a random variable, there exists an underlying sample space, which is giving you some elements. That is how you should look at it. Okay.
Sure, sir. So we're only talking about representatives right now. Got it.
Now the data. I mean,
Data. Yeah.
the
Sorry. Like data.
not labels. I'll come to the labels in a while. See, for instance, right, in generative modeling, you don't have labels, right? You
Yeah.
only have data. Let's look at the representation of data now from a random variable perspective. Then we will come to the labels in a while. Okay.
Yeah.
Any
Sure.
other questions on this? This is very important, right? I mean, this understanding is very important because from this is the last class when I'll be talking about the sample space. From like next class onwards, we'll only talk about random variables and distribution functions. So you have to understand like thoroughly what is going on. So if you have questions, so this is the opportunity for you to ask them. Any other question? Vivek?
So maybe the trick is in designing I mean, coming up with a correct probability measure for
See,
a given problem.
yeah. See, probability measure is. I mean, I didn't get your question. I mean, that was a sort of assertion, right? What is the question?
Okay. So, in one sense, I understand that this is still only talking about understanding uh, the basic data points, but when we move on to the next step, when we start try to assign labels, then probably we have to worry about a probability measure. We have to model that part.
Uh, Hold on. As I said, no, please try to, if you have questions on things that I've said already, do ask and let's not jump. I'll come to that. I'll come to all that
Okay.
in a while. Yeah.
Yes.
Um, any questions on things that we did so far?
Hello, sir. Can I ask one question?
Just a second. Yes, Sachin, go on.
So, sir, I was asking like this random variable function is like very important. If we are converting this sample space into some range space. So, as per our problem, like
No,
different
no,
problems will be.
hold on. Converting sample space into real numbers.
Yes.
Don't call it range space, real numbers. See, what is
Okay.
range? When you have a function, you have a domain and a range.
Right. Correct.
Uh, so random variable is a function that takes sample space and maps it to real numbers.
Hmm. So, for a given sample space, there we can define multiple ways, or we can define multiple functions. This random variable function, right? Based on our problem.
Very good observation. Yes, you can, and that is why that is a model. That's basically what a model is. So ultimately, we will see that the entire machine learning is about finding this underlying probability measure. Okay, why does the probability measure change? The probability measure changes because I mean when the probability measure changes, the random variable changes, right? You can,
Okay.
actually you can, yeah. So you can, there need not be one random variable corresponding to a random, a particular sample space. There can exist multiple random variables, yeah.
Okay. Thanks.
But what is important is that the moment you have some data, you should imagine that there has already been a random variable that has been applied to it. You understand?
Mm, no, like data is in its raw form, like images or speech or.
You have data. The moment you have data, you should know that there has been some random variable that has been operated on the sample space. In
Okay, okay.
practice,
If we have
what you
data.
get is
Okay.
data. Yeah,
Yeah. Okay,
got
okay.
it.
Yeah.
Huh?
Yes, sir. Got it.
Okay. Okay. Yeah, I think Bridge Gopal has a question again. Yeah.
Yeah, sorry, sir. Just a small one. It's a little different. The way you said, right? For a simple experiment like tossing a coin, we usually immediately associate a random variable with the possible outcomes like 0 and 1. We assign to head and tails, right? So, why so I'm assuming the reason we you choose 0 and 1 is that something to do with the probability measure and why did we choose 0 and 1 is my question. Why can't we have one
That's
or two?
arbitrary. That's arbitrary.
That's
You can choose
arbitrary. That's
anything. You
not
can choose anything.
okay. So that is not affected by our probability measure and our us wanting to keep it between zero
It, it
and
has
one.
it has nothing to do. No. Oh, that has nothing to do with the measure. It's the range of the random variable is arbitrary. You can choose it to be anything. In fact, it becomes a function of your sensor and all that. No, your
Okay.
quantizer, your sensor. When you take a picture, what values do you see in the picture becomes a function of what is the bit representation of your machine, what is the machine precision, what is the quantization that you are doing, and so on, isn't it?
Oh, okay. So maybe I'm merging two concepts. Okay. Thank you, sir.
So it has nothing to do with measure. Okay. 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 Let's move on. Now, the question is, once you have, okay, we understood what happens to the elements of omega when under the random variable. Okay. So now you understand why it is such a misnomer, right? I mean, keep calling it random variable, but you should imagine a function that's there. Right? Yeah, it's the biggest misnomer that I've ever seen. It's not a random variable, it's a function. Okay. Now, yeah, so we saw what happens to the elements of sample space under random variable. They get converted into real numbers, right? The next question that we should ask is, what happens to probability measure? So there is this probability measure, right? Once you operate a random variable, right, a function on the sample space, what happens to probability measure is the question. So you can always imagine this, right? So now, once an omega that belongs to omega, I mean, a W or W belongs to omega, right? And if you take that W and that is mapped to some real number, let's say. Okay. Now, what is x of omega? X of omega, right, is a real number. I'm assuming that you have a one-dimensional random variable in a while. Okay. We'll define that notion for n-dimensional random variables uh, after a while. Let's say that you have a one-dimensional random variable. If you take an element, a w belonging to omega, you will get a real number. Okay. That's what this random variable does. Now, suppose suppose um what do we call that, often run out of alphabets. Suppose small r is a subset of real numbers. Okay, examples can be -2 and 3, right, and like minus infinity to 2 and so on, right? All these are subsets of real numbers. Now, x inverse of r. What can you say about this? Let me repeat the question. We have a random variable, which is a function that would take elements of sample space and maps it to real numbers. Now, what I do is I take a subset of real numbers. You understand? I take a subset of real numbers, okay, and look at the inverse image. So this is the inverse image of R under the function x. This is the inverse image of a subset of R under the function x. What do you get from doing this?
Subset of omega.
Exactly. Yeah, you get a subset of omega from here. Can all of you see this? So this will be some set, okay, which belongs to F, which is a subset of omega. Can all of you see this? This is very important. Please let me know if you see this. Questions on this? I'm saying, suppose you take a subset from the real numbers, real numbers, a subset of real numbers, and look at its inverse image under this function. Then you will get a subset of omega. Is it clear? See, when I ask you a question, if it's clear, do respond. Otherwise,
Here, A is x inverse R. Is that the
come
representation?
again. Come
Are we
again.
using A to represent x inverse of the range subset?
Correct. Correct.
Okay.
Correct. Correct. A
Yes.
is the x. But what is that A? I mean, what's more important is that A is an element of F, where F is the subset of omega, right?
Yes, sir.
Uh, okay. This implies that we can talk of probability measures on the inverse of any subset of the real numbers. Okay, this is well defined, no? It is because this is equal to the probability measure defined on A, which is a subset of F. So this is well defined. Do you see this? So we can define probabilities on the inverse images of the subsets of real numbers taken under random variable. Let me write that. Probability of the inverse image of a subset of R under the function f is well defined. See, note that probability measure was a measure that was defined on the subsets of omega, sample spaces. Now, random variable maps the elements of that to real numbers. Now we come backwards. We take a subset of real numbers, okay, and we look at the inverse image of that subset of real numbers, under this function called the random variable that would give you an element from the sample space or a subset from the sample space. And on that, we have already defined a probability measure. Therefore, the probability of the inverse image of a subset of real numbers under the function called random variable is well defined. Did all of you get this? I'll take questions in a while, but yeah. Okay, one by one. Harish.
No, sir. So is it correct to say that these elements of A are the samples which are just sampled from this whole sample space? Or the
Elements
ones
of
which were just
no, no.
observed?
See, A is a subset. A is a subset. A is a subset. See, you remember this, no? There was an omega F and P. What was this F? F was set of subsets of omega, right? And on the elements of F is where we defined probability method. I should write that also here. Is that so? P is a function that is defined on A. Okay, that would take an element A, okay, which is a subset of F, and maps it to a number between 0 and 1. This is the measure that we defined, no?
Okay, yeah.
So F is set of subsets of omega. Okay, right? So we define the probability measure on the elements of F, which are the subsets of omega. Okay. Now we are saying that the inverse image of of any subset of R under the random variable will take us back to A, and on A probability measures are defined. Therefore, we can talk of the probability of inverse image of some subset of real number under the inverse of random variable. That is well defined,
Got it.
right?
Thank you, sir.
Okay. Sarvesh?
Yes, sir. So, since F is a set of subsets of omega, so A should be a member of F, right? Not a subset of F. Because anyways, all the subsets are there in F.
Thank you for that. Some mistake. That's my mistake. That was a good point. Thank you for telling that. Yeah, I actually meant that, but I wrote subset. Yeah, so that my mistake. Sorry. Thanks. Aviroop, did all of you get the mistake that I had done? I mean, that's A is not a subset of F. A is an element of F. Yeah, because okay, yeah. Aviroop,
Yeah, so when you say the inverse image, so are you referring to some notion called inverse function?
of course,
Because,
right? Absolutely,
okay,
absolutely.
okay,
Because
now,
X is a function, right? X is a function.
okay,
When a function always have an inverse, right? That would take an element from the range of the function and maps it back to the domain.
okay, now in that case, inverse function is also a function. A function by definition should always have many to one or one to one mappings. But in this case, we are having multiple elements from the domain and we are mapping them to a set, which is
No,
a, okay.
no. See, when you take when you define the random variable, right?
Mhm.
You can make it a bijective function so that the inverse exists.
Okay.
Yeah. So you take every element from the sample space and map it to a unique real number.
Okay.
That's all. So then it becomes invertible, right? It's a bijective function that can be inverted.
Is it always possible to come up with a random variable which
Of
will,
course, why not? Because random variable is something that we are defining, no? You always make it bijective by definition,
okay,
right? So that's why the inverse exists.
okay,
Hmm? So basically what I'm saying is this function random variable always maps a unique element from the sample space to a unique element in real numbers. That's all. Yeah.
okay, okay,
Yeah. See, in fact, even if it's not a bijective, right? Only subjection is enough for inversion, but you can make it bijective. Nobody stops you. Yeah.
okay,
Because functions like f of x squared, sorry, f of x equal to x squared, right? Even those have inverses. So, but now for ease of understanding, let us assume that our random variables are all bijective functions. Okay. Yes, Sanchit.
Sir, as per my understanding, we have random variables map the individual outcomes in the sample space to a real number, right?
Correct. Correct.
Now, in the example we have taken, we are saying that we have taken a range -2, 3 or minus infinity, 2, and
Hmm.
that we are mapping to a subset.
Hmm.
So I agree that this subset A, this can be individual elements, but I'm not able to digest that this subset can have multiple elements of the sample space.
It can, no, because it depends on the way your function is defined, isn't it? See, it's
Okay.
like this, I'll tell you. Suppose there is a function, right? Let's say f of x is equal to say x plus 3. Huh? Then what is the mapping? 0 to 3, and then you have 1 to 4, 2 to 5, and so on, isn't it? Okay. Now suppose I take a set which is, let's say, 4 to 8. Can't I define this?
Okay, so this will give us a range of x.
Isn't it? Exactly, no? It gives you a
Okay.
subset of the domain.
Okay.
So,
Okay, sir. Makes sense.
yeah.
Yeah.
That is why the inverse
Hmm.
image of a subset of R will give you an element from F, not an element from omega.
No, so
Because we are not.
that's what the confusion, like that's what I said.
But do you understand? No, no, what I'm talking about. It gives an
This
element from F because we are talking about subsets in the range space of the random variable that gets mapped to subsets in omega. That's all. Yeah.
okay, if our domain is only the subset, then anyways, it will
No, no,
give
no.
us
What do you mean by domain is subset? I didn't. Domain is
in
a
this.
set. Domain is a set. But what you are saying is if I consider subsets in R and take the inverse image, I get subsets in omega.
Okay.
But if I take a singleton here, I mean, if
Hmm.
this set has one element, perhaps I get back one element there, right? And note that a set here, right, a subset of R here might map back to null set also. That's
Correct. Correct.
also possible. Yeah,
Correct.
but
F.
that's also a subset of R. See, F also contains null, no?
Hmm.
So
All the
that's why I
possible
don't care.
subsets of
Subsets of
omega.
omega, and null is
Hmm.
also a member of F.
Correct.
Therefore, the inverse image, that's why, in fact, probability measure is defined on null set also. The probability of a null set is 0.
Correct.
Yeah. So that's why it's well defined. You can take a subset in the range. So basically what I'm saying is that you can take a subset in the range space of random variable and the inverse image of that will map back to an element in F. That's all, no?
Okay. Okay. And that element, it can be a singleton or
Doesn't matter.
a
It can be
subset.
null. Yeah, it can be
It
null.
can
It
be
can be a
anything.
sin. That is why I'm saying it's simply a member of F. That's all.
Okay.
So why does
Okay.
it have to be an element in F but not say a subset of sample space?
Same thing, no. Subset of sample space is what we have denoted as F. All
But it
possible
has to be
subsets.
an element in F, right?
Of course,
So
all
for
subsets
instance,
of,
if
see,
I
F
all
is a
if I
set of
subsets of
increase
subsets.
if I
F is a
increase
sub.
the range, so you have put -2 to 3, and now I change it to say -2 to 5. So now does it have to belong to only one element in F?
It'll get to a different, it will map back to a different element in F, no?
But an element in F, not
Of
a
course.
subset of subspace of
Okay,
sample
subset
space.
of set of subsets of sample spaces is what we have called as F. F is nothing but set of subsets of sample space. What is F?
Okay, so it cannot map to multiple elements in F is my question.
It cannot map, of course, right? Of course, right? If you take a unique set in the unique subset in the range space of any function, the inverse image will map to a unique subset in the domain of the function, right? If the function is bijective.
Yes.
Yeah. Simple. I mean, see, this is like your high school function. I don't know, when did you study functions? Was it in high school? I studied it in class 11. What about you people? I don't know. Yeah. Are we different generations? Perhaps, no? You mean most of you may be like between 20 and 30, I suppose, right? Most of you. Yeah, I have crossed 30, so maybe I'm of it. Every decade is a different generation, you see. So every decade they change the syllabus and all that. So I studied functions in, when did I study functions? It was in class 11. When do the teacher teach them these days? High school? Did anybody study functions in high school?
Yes, sir. 11th
Yes,
only.
sir.
Yeah, 11th is not high school, no? Yeah. It depends. I mean, what curriculum are you a part of? I was in the state board, right, where this 11th was called college for some reason. It was called pre-university college. Anyway, okay. So I'm saying it's just fundamental stuff, right? You have two sets. I'm talking about inverse images. The one thing that we introduce new, perhaps, is that this is the idea of measure. Okay. Okay. So clear so far. Okay. Now consider consider subsets of R of the following form. So let's say R1 is a subset of R that is equal to minus infinity to R1. Again, overloading notations here. Let's not do this. Let's call this as S1, and this we will call as, yeah, we can call it R1, no problem. And this S2, just strictly speaking, it is non-inclusive of this. You understand this notation, right? This set includes minus infinity, does not include R1. It's upper bounded by R1. Here, this set includes minus infinity, but
Sir, how can we include minus infinity?
why not? It's an element in R, no?
It is, but it is not defined, right? What like
No, very much defined. Why not defined? It's an element in R. You can definitely include minus infinity, no problem with that. Okay. So let us consider these sorts of subsets of R. Now, yeah. Now, X inverse of S1 is what is some element in R, no? Let's call it as A1, which belongs to F. Okay, right. Now, the probability measure that is computed on the inverse of subsets of this particular type, one, two, no, this is for this is for this, we need one more bracket, this, okay. This is well defined, right? You understand? What is this? This is the probability measure that is computed on, that is assigned to the element of F, which is gotten by the inverse image of this set minus infinity to X under the random variable X. Okay, maybe not use X here. Again, it'll make life difficult. Let's call this as A. Okay. Is this clear to all of you? This is a well-defined measure, no? The probability assigned to an element of, oh, by the way, have I already said this? This is also called the event space, okay? F has a name. It's called the event space. So this is the probability measure assigned to the element of the event space that gets mapped to that gets mapped to a set minus infinity to a under X, or rather, it is the probability of the event or probability of the member of the event space obtained by taking the inverse image of this subset minus infinity to A under the random variable X. Do you understand this statement? If you understand this statement, then you have understood everything that I've said so far. Shall I repeat this statement? Okay, let me write that down. Maybe it's better to write it. This is the probability of the element in F in the event space that is obtained obtained by taking the inverse image of the set minus infinity to a under the random variable x. Is this clear? Any questions on this? All of you, please ensure that every one of you understands this. Nirmaj,
Sir, can you explain what is under the uh,
random
inverse image
variable
of
x.
x? Yeah.
X is a
Yeah.
function, no? See, when we talk of inverse images, we have to specify what function are we looking inverse images under.
Okay.
See, when you take a subset and you talk of inverse images, what is the function under which you are taking the inverse image? It is a random variable, which is a function, correct?
Okay.
Right?
Yes.
Yeah.
Is it does it mean that, let's say, if we take S of some sample space, we'll reach out to a particular range? If you take inverse of that, whatever the sample space or the event space that we end up in, probability of that is what we are defining here.
Exactly. Exactly. But we are looking at particular subset of real numbers, no? This particular subset. The kind of subset that we are looking at is like close minus infinity to open A.
Okay.
Right? Karthik Kumar?
Yeah, sir. So, does A have any relation with the
Your voice is
R1
breaking
that we
here.
defined for S1?
Karthik, your voice is breaking.
Sorry, am I audible, sir?
Yes, now.
Am I audible?
Is
Yeah,
it only
sorry.
for me?
Has A
His voice is breaking.
No, for us also.
It is me.
Karthik, can you?
is it still breaking, sir?
Yeah, not now. Try now.
Yeah, I just wanted to ask, is A anyway related with R1 and R1 which we defined S1 with minus infinity to R1?
Well, it is in the sense that this particular R1 is this particular set is the one that maps back to A1. That's all. Other than that, there is no relation per se.
Okay, so yeah, I mean like
If you take this particular subsets and take the inverse image of this, it will go back to A1. That's all.
okay, yeah, sure. Thanks.
Okay. Okay, great. So this let's give a symbol for this. Let us call this as Px evaluated at A. This is a symbol, okay? What is it saying is, I mean, I just represent this complicated looking thing using a simple symbol, right? I mean, this symbol actually means that I am looking at the inverse images, the probability of the inverse image of this particular type of subset minus infinity to A under the random variable. This is the symbol. Is this okay? I'm just using this symbol for this complicated thing. Is that okay?
Yes, sir.
Okay. It turns out that this has a name. This particular thing has a name, which all of you know. Do you know what the name of this is?
PDF.
Exactly. No, not PDF. This is the
CDF.
cumulative distribution
CDF.
function. Yeah, this
CDF.
is the distribution function. This is the distribution function of a random variable. Some people also call it the cumulative distribution function. I mean, I don't know why it is called cumulative. You don't have to call it cumulative, okay? But this is called the distribution function of a random variable. Is this clear? So
Sir,
what?
since it accumulates the distribution from minus infinity
No,
till
no, please. I said there is no accumulation that's happening. No, see, the reason perhaps why people call it cumulative is because you define a density function and then you can represent this function as a running integral of that other function, and that's why it's called cumulative. But I'm not a fan of this term cumulative. I mean, standard textbooks call it a distribution function, and yeah, this is a distribution function. Okay. Now, what is the distribution function? It's the probability of the element in the event space that is obtained by taking the inverse image of the set minus infinity to a under the random variable x. So if you evaluate this distribution function at a value x or a, you should remember that you are actually looking at the probability of an event, probability of an element from the event space. What is that element? That element is the one that you have gotten by taking the inverse image of this set minus infinity to a under the random variable x. Is this clear? This is the single most important definition that we'll be looking at, because the entire machine learning is estimating this particular function given elements from range space of random variables. That is all the be it generative models, discriminative models, classifiers, regressors, anything. The entire machine learning is about estimating these functions, the probability density functions, sorry, distribution functions. Okay, so in fact, instead of calling it cumulative distribution functions, no, let us call them the probability distribution functions. That is much better name. Probability distribution functions. Probability distribution function of A. Is this clear? Please remember that if you evaluate the distribution function at a particular point, okay, if you evaluate the distribution function at a particular point, what are you actually doing? When you evaluate the distribution function at a particular point, you're actually getting a probability. Probability by definition is defined on the elements of F. Now, evaluating distribution function at a particular point should give you, right, the probability of a particular element in F. What is that element in F whose probability this function is giving you? It is that element in F, okay, or rather that subset of the sample space, which is getting mapped to minus infinity comma a under the random variable x. Is this clear? Please remember this, huh? Because as I said, no, this is the single most important definition that we need for this course. So yeah, questions on this, Sanket?
Sir, this probability distribution function is usually the probability at a single point, right?
No, definitely not. I mean, that is precise 3.5 hours to define this. It is not that. See, point number one, I am not talking about probability density functions here. I am talking about the probability distribution functions.
Okay.
Okay. And even probability density functions are not probabilities. Please remember that probability is a measure that is defined on elements of F, period. You cannot talk of probability of X being equal to something. It just does not make sense. You understand? Because by definition, probabilities are defined on elements of F. That's all. See, it's like, can you talk of length of okay, what do I say? Hmm, yeah. If I say, length of water, right, or length of speech or something, it's just not defined, right? Length is defined only on elements of subsets of R, isn't it? Similarly, probability is a measure that is defined only on subsets of omega. So whenever you talk of probabilities, you should always make sure that you are talking about the probability of an element of F. That is why this distribution function, while it is denoted as Pxa, okay, this actually means this entire thing. Whenever I write Pxa in this course, you should always remember that I'm talking about this. Okay, you should remember that there exists a function called random variable. Okay, and this random variable has an inverse image. The inverse image of, we are considering the inverse image of this particular set minus infinity to a. Now that gives you an element in the event space that has a probability associated with it, and that is what this function is giving me always. Okay. Is this clear? Because I want to make this damn clear to all of you, because people very wrongly say that the probability of a random variable, there is nothing called probability of a random variable. Okay, it does not make sense. You mean it's like saying round circle or something. There is no probability of random variable. There is probability of elements of f. So if you evaluate the distribution function of a random variable at a particular point, what you are actually doing is this entire thing. Okay, please be clear about it. Rajat.
Hello, sir. Sir, my question is, when we are taking the inverse of a subset of R, then it might not be having any element in F, right? For
No, it
example,
will always be. It will always be. It will always be. It
suppose
can.
tossing,
Go on.
yes, example, tossing a coin will have outcome of head and tail. And suppose head is translated to 0 under random variable and tail to 1. Then if I try to take the inverse of, for example, 3,
2.
which,
Yeah, then it maps back to null. That's all. And null is also an element of F.
okay, got it. In that case, probability will be
0.
Okay,
Absolutely.
Got it. Thanks.
Actually mentioned this, maybe you missed that. No problem. Avirup?
Yeah, so I understood this definition, what you just mentioned, but I am a little bit intrigued how we actually find the value of PXA, because that would involve finding the event.
Hold on. I
Okay,
will not come to that. See, please, again, I am reiterating, don't jump. We will not leave anything in this course. Okay, we will address all those questions. Okay, but see, when I ask you for questions, right, please ask me questions on things that we have discussed so far. Because otherwise, right, if you jump ahead, then it'll sort of break the flow. Please don't take it in a negative sense, huh? Just to ensure that we are going systematically. That's a good question, by the way. How do we estimate PX? Is the question that we ask in machine learning. All machine learning is about estimating this distribution function. Okay, so don't worry, we'll come to that in the next part of this class. Indrajit?
Yeah, when you say you are taking probability of inverse random variable minus infinity to a, can
Indrajit, just a second. Please use correct terms. There's no inverse random variable. So can you say it correctly? The probability of just attempt. No, say it correctly.
So inverse probability of a real number?
No, not the inverse probability. See, inverse is defined for a function.
Yeah, okay.
Inverse is defined for a function. Okay. Inverse of the function called random variable over a set. That is how you should say it.
Yeah, so when you're taking that set as minus infinity to a, can it be any other set, say a1 to a2?
I'm glad that you asked that question. I wanted somebody to ask this. It's a very good question. So why are we considering this particular set? What's so nice about this particular set is the question that you are asking. Correct?
Yeah.
Yeah. I'll answer that next. That's the next thing that I'll do, but I'm glad that you asked that question. I'll answer that. I was expecting someone to answer that question, ask me that question, right? Why it is so sacrosanct about this particular set that we are assigning a function to it, right? I mean, or rather, like we are giving it a particular name. What is so important about this? I'll answer that in a while. Okay. Okay. Raghavendra?
Yeah, sir. Why does that interval not include a?
See, is related to the other question that Indrajit asked. Okay, what is so? I mean, why is this particular set, right? That is the next question. Okay, we'll answer that question perhaps. Now it turns out, I'll just state that without the proof. Maybe, yeah, okay. By the way, there is one other convention. I'll tell you that. Why? Right? This question has to be answered. So the answer to this is, it turns out any subset in R can be represented as via set operations or sets of form so this, okay, so here is the convention, okay. So from now on, whenever I state something, okay, without proof or without giving you a lot more details, I will mark them as tutorial items, okay. Now, I ask one of you, like, or maybe all of you to take a note of it, okay, and just put it in the Teams as tutorial items, and this has to be covered in the tutorial by TAs. Huh? I'll keep doing this from now on. Okay. Anyway, so the thing is, any subset in R can be represented via set operations over these kinds of sets. That is the reason we are interested in this kind of set. What does that mean? That means that suppose, or rather, so if you take a set, subset AB, okay, that is in R, this AB can be written as yeah, this is such that is equal to A.
Sir,
Right?
we
I'm
need
just
to have square braces for A comma B, set A comma B.
because that is those are included, no? Yeah. I think what I had written earlier was correct. There's one example. I think like TS will do a proof for this. So basically, what I'm saying is that if you can take any subset in R and that can be represented using the set operations on these kinds of things. Okay, and we know that probabilities measures, probability measures will add up. So therefore, if you want to take if you want to look at the probabilities of, let's say that you are interested in the probability of the inverse image, okay, of this particular set, this can be obtained in terms of the the distribution function that is evaluated at B, subtract that with the distribution function that is evaluated at A. So again, the proof of that shall be done in the tutorials.
Sir, B is not
Okay,
included in that interval, right?
B is not included in the interval. Is that so?
Yeah, because it's not
B is
included in
A is
minus
included.
infinity
A
to
is
the B.
included. B is included. So yeah, A is included. B is not included. I think this should be correct. Correct. This is what you're saying. B is not included
Yes.
in the interval. Correct. Okay. Yeah. So this is why we are interested in this particular set. That if we want to look at the probability of the inverse image of any subset of R, okay, we can obtain that in terms of the probabilities of events that are associated with the inverse images of this kind of subsets. Okay, that is why we are interested in this particular type of subsets. Okay, does that answer your question? I think Indrajit asked this question, and why are you interested in this particular subset? Is because of this, that we can obtain the probabilities of inverse images of any of subset of R using these subsets. Okay. Now, what is this has a very big implication? This implies that the probability distribution function completely completely specifies the underlying probability measure. Right. So what I was saying is that if you know the distribution function, then you know everything about the underlying probability triplet. Can I make that statement? So basically what happens now, that you start from, this is what you have, which is the probability triplet. You have the sample space, the event space, and the probability measure. Now this, when I operate a function called random variable on top of this, okay, what happens is this will induce another measured space, that is called also called the push forward measure. This will map omega to R, and it will map F to subsets of F, okay, which are subsets of R, which are also called the Borel sigma algebras. Don't worry about it. It's just a name given to specific subsets of R, and the probability measure gets pushed forward to distribution function. This is the story. Okay. Now the thing is, in practice, no access to this. We don't have access to this. Okay, but this is accessible. The data that we get are actually the members of this R. Okay, so now when we have like thousands of images, they're all members of this R. Okay, now because we have this, we always operate with R, B, and Px. We don't even look at B, R, and Px. So now if we get Px, then we know everything about the underlying probability space. Okay, this is, by the way, this is also called the probability space or probability triplet. Okay, and this is called the push forward or induced space. It's actually a space that is induced by a function on the sample space, no, which is called the random variable push forward or the induced space. So we simply work with this, accessible, and work with this. See, work with distribution functions, right? And the elements of the range, elements from the range space of random variable, that's our data. Okay, that is our data. But you should always remember that whenever we talk of a random variable and a distribution function, you should always remember that this random variable is a function that has an underlying probability space. Okay, and the probabilities that we are talking about are on the elements of that F event space. Okay, this is the clarity that you should have. So in other words, if we know what the distribution function is, then we know everything about the underlying probability measure. And that is why entire machine learning is cast as estimating the problem of estimating the probability distribution function given data. I will write down all this, right? Yeah. So I just wanted to tell you that why are we working with random variables, and what are random variables, and what are distribution functions. Hope that you people are clear about this. Okay. Questions now. Sanchit.
Sir, why are we taking the concept of Borel sigma algebra here?
Because when you have this random variable, right, that would take omega to r, f,
Hmm.
right, get pushed forwarded to Borel sigma algebras.
So, like for Borel sigma algebra, what understanding I have is it will have all possible subsets of the form A, comma B.
Correct. 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 True. That is why f gets, because those are the elements, those subsets of R gets mapped back to elements in F. No, that's why the push forwarding that happens from F via a random variable is Borel sigma algebra.
Okay.
I'm not telling you that because, as I said, no, you can mostly ignore this B, because we are basically, what I'm saying is, when omega gets mapped to R, what happens to F? F gets mapped to Borel sigma algebra. That's all.
Then, sir, by default, the probability measure should be a length measure, right?
No. Yeah, not necessarily, because probability measure is defined on the probability triplet. No, but I mean, that's a good question that you ask. See, we can integrate distribution functions, right?
We can what?
Integrate distribution functions, we can differentiate distribution functions, right?
Correct. Correct.
Operations of integration and differentiation are defined on Lebesgue measures. That is one of
Length.
the reason. Yeah, length measures. No,
Hmm, hmm, hmm.
operations of integrations and differentiations are defined on the length measures, Lebesgue measures.
Correct.
Now, since that is one of the reason why we need a random variable. See, you cannot integrate in the probability space, because integration is in probability space is not defined at all. Right? So once you get to the push forward or induced space, you can do integration. That's why you can differentiate the distribution function and you get another function called the density function, right? You can integrate the distribution function. You can do all those things. The default measure is not the length measure. The length measure is defined only on Borel sigma algebra. Okay. Under the random variable, right? Once you do the push forwarding, you get the Lebesgue measure. Before that, it's the probability measure only. Got it?
Sir, so once we have an induced probability space, we have a Borel sigma algebra and correspondingly the Lebesgue or length measure.
Correct. But we are not interested in the length measure on the Borel sets gotten from the push forward induced space. We are interested in the probability measure that is obtained by the inverse images on the subsets of R. Because we are interested in finding out the underlying probability measure, not the length measure of this Borel space. Okay?
Okay. Okay.
Because the whole purpose is to model that picture and map it to a gender or something, right? We are not interested in the Lebesgue measure of this push forward space. We are interested in these kinds of induced measures, right? Which are called the probability distribution functions. Yeah.
Okay.
Okay. So rest of the people can ignore this discussion if it didn't make sense. Okay. So don't worry. I mean, that was like slightly off topic. Okay, Divyang.
So the induced space, we have data. So this probability Px, that is calculated based on the data, or it's available exclusive otherwise also?
No, it is not available. No, the whole problem of machine learning is to estimate this px. We don't have this px
Correct.
with us.
Okay.
I will say that. See, what we have are the elements from the range space of random variable. That's all. That is our data. The whole
Px will
problem of
be
whole problem will be to estimate px.
correct.
Entire machine learning is estimating px. Okay.
Yep. Got it, sir.
Well, I will define that. I will define that in a while. Yes, Raghavendra.
Yeah, so in general, do we also know X always, or?
No, we will not know x. We will only know. We will only have elements from the range space of x. We will not know x. See, when you have images, right? What do you have? You have a lot of real numbers, right? Each image is a set of real numbers. Correct.
Yes.
What is that? That's actually the elements from the range space of random variable. You don't know what the random variable is.
Correct.
Right. I'm telling you again, random variable is not a variable, it's a function. So please remember that. Okay. Is this clear? Sanchit has one more question. Yeah, Sanchit.
Sir, so basically, we have a probability triplet, and in order to have an ease of operations, we are inducing the concept of random variables, and
Correct.
with that,
Not only that, right? Ease of operation is of course one because we can integrate and all that. There is one other reason, no? The way I motivate it is you don't have access to omega FP. See, in real world, what do you have access to? You have access to real numbers. How do you see real numbers as elements of omega? No, you can't. There is
we just
something that is there is
we
something
just
that
have
is
the out,
huh.
we just have the outcomes that are
We
known to
don't
us.
even have we don't even have the access to outcome. We have access to some measurement of the outcome.
Correct.
And how do you quantify that? Using math. That is quantified using random variable, no?
Correct.
So basically there is a function that is sitting on top of the outcomes, which is giving you the real numbers. That is what we have access to.
Correct.
And now, since we have defined the probability measure on the subsets of outcomes, we need an equivalence in the induced space, and that is
In
your
the induced
distribution
space.
function. That is your distribution function.
Got it, sir.
Yeah.
Got it, sir.
Yeah, but always remember, no, this definition is very, very sacrosanct. I mean, you should remember this. Whenever I talk, I will be talking of distribution functions all along the course now. Okay. Whenever I talk of distribution function, you should remember this. I suggest all of you go back today after today's class, sit down, maybe rewatch the lecture, and try to get this idea solid into your mind. Okay, very, very important. Lot of people handwave on this and wrongly represent distribution function as probability of random variable. That does not make sense at all. Huh? So please get these ideas uh, nicely into your mind. Okay. Indrajit?
Yeah. Does it really matter whether we include A or B endpoints or exclude them?
Here,
Yeah.
it depends. No, you can take any set here, and as I said, any set can be represented using these kinds of sets. That's all. You can take any set. You can take the inclusive sets, exclusive sets. Doesn't matter. You can represent any set like this using these kinds of sets. Operations on these kinds of sets. Okay.
Yeah.
Okay. Great. Okay. Rich Gopal.
Hi, sir. So let's say using machine learning, we have successfully approximated PX, which gives us basically the ability to tell how probable it is that we'll see a set a subset of event space A in real life, correct? Up to this point, am I understanding? So how does this understanding translate into us knowing about the actual underlying P of the
So
probability
that is
space?
your P, no? That is P. What is P? P is the probability of a particular subset in F. If you know that, you know that. That's all. See, maybe you should ask a different question, right? Why? How is that P important or relevant in telling what is the gender of this particular person is, right? Obtained from that image.
Yeah.
That question I have not answered yet. I will answer that question. But if you estimate the probability distribution function, then you know everything about the underlying probability measure.
Okay, so just I'll say a statement. Please help me understand where I'm going wrong in this. So once we approximate PX, so I'm thinking of PX as a function that takes an input and generates an output. So the output that is generated is a part of P.
What do you mean by output? I didn't get that. See, the probability distribution function is a function. I agree, right?
Yeah.
Whose range is 0 to 1.
Yeah.
Now, what is the question?
So from the definition of PX, what we get is the likelihood of observing A.
Have I defined the term likelihood?
Okay.
Please don't use the term because all those are mathematically precisely well defined. Don't use the terms that are not defined.
Okay, so
if you evaluate the distribution function at a particular point, it will give you the probability of the inverse image. That's all it is. Now,
yeah,
what is the question? Yeah.
so the probability of inverse image, or to go with the notations, probability of the output, correct?
No, again, there is nothing called probability of A. This is a notation. When I evaluate the distribution function at A, what am I doing is I am looking at the probability of inverse image of this particular subset. That is all it is. There is nothing called probability of A, please. That is the misrepresentation that I want to take out of your minds. When you evaluate the distribution function at a point, okay, you are not getting the probability of that point. That does not even make sense.
Sorry, sir, I was not talking about small a, I was talking about capital A, the set.
Oh, sorry, my bad. Yeah, it is the probability of A, correct. A1, I have set it as A1, no? Yeah.
Yeah, okay, A1.
Yeah.
So now the probability of A1 is actually that underlying P, correct? That we were talking in that first triplet.
Yeah, of course, no, P is a function. This
Yeah.
P is a function that will take an element of F and gives you a number between 0 and 1.
Got it. So
It's a method.
Yeah, so am I correct in my understanding that the output of Px on small a is actually something in the P on the left hand side of this
That's correct. That's precisely correct. Yeah, if when you evaluate the probability distribution function, right, at a particular point A, it will give you the same output that the probability measure, right, would have given on the subset A1. Correct. That is correct.
Okay. Yeah. Thank you, sir.
See, that is why capital P, right, is a function that would take elements of F and map it to 0, 1, correct? And probability distribution function, okay, will take an element of R and still maps it to 0, 1.
Yeah.
You notice that the range space of both of these are same.
Yes.
By definition. By definition.
Sure, sir. Yeah. That clears it up. Thank you.
Yeah. Okay, thanks. Okay, anything else? So take home message is the following, right? When you take the distribution function and evaluate at a point, what does it give? Probability of the inverse image, right, of the event that is obtained by taking the inverse image of this particular set minus infinity to A under the random variable X. This is the take home message. Remember this. How do I highlight this or something? Does it stay? It stays. Hold on. Make it in red. It's super duper important. Okay. Oh, does red means that this is wrong or something? No, it's not use red. Use some other color. Yellow is okay. Green.
Sir, if you change the paper color, then it will be more visible.
From black to white,
White or yellow. Yeah.
Okay. This is fine. Yeah. So please remember this. This is the message that I'm supposed to give today. Okay. Fine. Okay. Shall we break for 15 minutes?
Yes, sir.
There is one other nice question that I was expecting. Nobody is asking me. Anticipated an answer. It is 10:45 in my clock. Let's get back at 11 p.m. Okay. So 11 a.m. Okay. See you in 15 minutes. Hello, shall we begin? Continue. Tell me this, show of hands, please. Is there anybody who has not studied a probability theory course in your undergrad? Like no probability theory course at all. Is there anybody like that in the class? Can you raise your hands? There is somebody like that.
So can you repeat?
So is there anybody who has not taken a probability theory course like ever in your life, undergrad or something? Okay, nobody. Good. The reason I asked is that, see, all of you know these things, maybe in different forms, right? Maybe not this rigorously or in different forms. I just am trying to give you a different perspective. That's all, right? So, yeah. So you people are aware of these things, no? That cumulative distribution functions. You have heard these terms and like you have worked with these, correct? Gaussian distributions and all this. Have you? Most of you have worked with these things, right? I mean, you are aware of these things earlier. That's good. So as I said, no, the first 2, 3 classes, initial 2, 3 classes, I think I develop the language and give you perspectives of how I would like to see things, and then from then onwards we can take off very quickly. Okay. Let's get back. So now we have the probability triplet and we have a reduced space, a distribution function associated with it. Now, I mean, we are opening the Pandora box of probability theory now. It's too many things that come up. I'll just define a few things that are kind of obviously needed for our course, and then we'll move on. So the first thing that I want to talk about is vector valued random variables. Again, another misnomer. Okay, so vector valued random variables. These are random variables, right? That such that the range space of this function that we are talking about is Rd and not R, the vectors. Okay. Do you understand? So what is happening is the elements of sample space now gets mapped to d-dimensional real numbers, not one real number. All the while we were looking at like real numbers here, right? The mapping was to real numbers. Okay. Now, in a vector valued case, which is our general case, right? When we have images or like embeddings of text and speech, etc., they are all some d-dimensional vectors. So these are like they are called vector valued random variables because the range space of the random variable that we have will be vectors, d-dimensional vectors in general. Any questions on this? Great. So in this case, right, when we evaluate the distribution function, right? The distribution functions gets evaluated at a vector A, right? So now the argument for the distribution function will be a vector A. I will not be using this head bar after that. I mean, this is just for once. Okay. So how do you define this now? This is the probability. Okay. So let us take an example and do it perhaps easier that way to show. So example, suppose the random variable is two-dimensional. Okay, maps the sample space to two-dimensional real numbers. Okay, now what happens to the distribution function of this? By the way, the notation that I usually know, this is the notation that I'll be using. When I write this subscript, okay, that denotes the random variable. Okay, and whatever is within the brackets is the value at which we are evaluating this. So now how should I evaluate this? X, what should I write inside the bracket now?
X inverse and within brackets the vector.
No. I'm evaluating it at a point. No, the notation is that probability density distribution function is evaluated at a point. And what is this point? No, this point is now some vector a1, a2, correct?
Yes.
All of you with me on this?
Yes,
Because the
sir.
random variable is a two-dimensional random variable, distribution function is evaluated at a vector. Now again, we'll interpret this. Now, what does this mean? This is the probability of what? Again, our own notation, right? It is the probability of the inverse image under X. Of what set are we considering here? Can somebody tell me what is this set? Do you understand?
Infinity to
Huh?
a1 minus infinity to a2.
Minus infinity to
a1 and minus infinity to a2.
no, what should I? This is one set. What should I write? I should write a bracket here. What should I write?
In
This
physical
is also a vector.
representation, we understand it's an area, sir. Like
So what should I write here? Tell me. How should I write that set?
Cross.
Yeah. Okay. So does all of you understand this? What is this cross? What is this cross? Or the Cartesian product. Yeah. I'll just tell you what that means. See, in one dimension, if you have a line, there is an A, right? The set that we are talking about is minus infinity. That would end at A, correct? So this is the set that we are talking about. Minus infinity to A is this particular set, correct? Now in two dimensions, if you take a point like this is A1 comma A2, right? What is the set that we are talking about? Now we are not talking about this as the subsets of R2. They are not lines. What are they?
Area.
Area.
What to call them? Areas.
Planes.
Planes. Yeah, they are planes. Okay, first of all, subsets of R2 are planes. Okay, so what sort of plane are we talking about? So let's say that we have A1 comma A2 here. This is where we are evaluating the distribution function. What is the set that I just wrote? What does that correspond to?
Sir, or anything to the left of
This is
A1.
this is A2. Okay. And this is A1. Now tell me what is the set that I'm talking about?
Towards the
All
left of
quadrants.
line A1 and below the line A2.
Exactly. So this line, this space, this entire space which extends infinite to infinity to in the left direction and to infinity in the bottom direction. Is this clear? So this set is the Cartesian product of is all of you clear? Now we will not be working in two dimensions. We will be working in like 10,000 dimensional space because our image is in 10,000 dimensions. So when I evaluate the distribution function at 10,000 dimensional point, a vector at 10,000 dimension, you should remember what is the inverse image that it maps to. It's a Cartesian product of like all those things. Do you see that? It will be a hyper volume in that dimension. Is that okay? See, when I evaluate the distribution function at a particular point in some 10,000 dimensional space, I'll be looking at the inverse images under that random variable of a certain hypervolume. What is that hypervolume? That hypervolume is given by this sort of a Cartesian product. No, minus infinity to the first element cross, minus infinity to second element cross, minus infinity to third element, and so on. That becomes a hypervolume. In three dimensions, I can tell you what that is. No, it's a huge three-dimensional volume, right? In four dimensions, I don't know what it is. Just call it hypervolume. Is that okay? So we'll be working with such distributions. We'll be working with random variables whose range space happens to be in some d-dimensional real space. If it's an image, then it is some 10,000 dimensional. If it's see, what is the size of the embedding in BERT kind of models? Is a few hundreds, right? Or few thousands, I suppose. Can somebody tell me? In BERT kind of models, what is the size of embedding vectors that you get for each word? Just Google that. BERT embedding size.
512.
Somebody, is it 512? Let me check. Size. 768 length vectors, BERT base, and BERT tiny gives you 128 dimensional vectors. Yeah, of order of 100. So that is your that is the dimensionality of the range space of the random variable that you will be working with. Is this idea clear to all of you? Any questions on this? So from now on, we'll be working with vector valued random variables. Okay, not the scalar, which means that the elements of sample space gets mapped to a d-dimensional real number. Okay, great. Products, Cartesian products. Okay, fine. Now the next thing that I want to talk about is that why doesn't it come to the middle? Fine. B. Talk of multiple random variables. Okay. Now suppose there are two random experiments that are happening. Let me give you an example. What I do is first there are okay, I'll give you a simpler example. There's a coin that is being tossed. Okay? And there is a die that is being rolled. TYE or DIE? What is it? TYE, is it? No, DIE.
I
TYE is color, I suppose, no?
Yes, sir. It should be DIEs.
DIE.
If it is singular, it should be DICE.
Dice, correct.
Sir.
There's a dice being rolled. Okay. Thanks. Yeah. So now what happens is, see, both of these will have their own sample spaces and underlying probability measures, right? Let's call this P1. There's another sample space, another uh, event space, there's another probability measure, correct? True, right? Now what I can do is, can take an element A, okay, belonging to F1 and an element B that is belonging to F2. Okay, I can do this. So, hold on, I'm just thinking, is this the best way to take home this point? There are other way to do it. maybe this is not the best example. Yeah, this may not be the best example because unions and intersections, no, that would create some lack in understanding. Better to talk that there are two random experiments, okay? So which is like, let's say rolling two dice of different configuration. I think this would be a better example. Yeah. So this can be a good example that here what we are doing is that we are rolling two dice of different configuration, which means that there are two sample spaces again and two different probability measures. Two, okay. Now again, if there is an element that is in F1 and an element that is in F2, right? Because these are sets, we can talk about unions and intersections of these, right? Can you see what I'm talking about? We have two random variables. We can talk about unions and intersections of these events, right? These subsets or these subsets of different sample spaces. Now, because we can do that, there are a few things that are being defined, which are like something called you can define a probability measure on unions. In fact, see the unions and intersections may not be on two different sets, right? I mean, unions and intersections may be on uh, like one random variable as well. Unions and intersections may be on a single random variable as well. But yeah, let's say that we are defining unions and intersections of the elements of outcomes from two different random variables. You can always talk of probability of unions and probability of intersections and so on. There's also this conditional probability that is defined. No, it is defined as A conditioned on B. You know the definition, right? It is the probability of the intersection divided by the probability of conditioning event. This is how the conditional probability is defined. All of you know this, right? That's why I asked you whether you people know probability theory. This is known, right? All of you know this? Okay, great. Now, what I wanted to tell you is because we can define like conditional probabilities and unions of probabilities on outcomes coming from two different experiments. Now what happens is there are two probability spaces. Okay, there are two probability spaces, which means that there are two induced spaces. Let's call them X. This gives rise to one distribution function. Okay. There is another sample space and the corresponding probability measure. Let's call that Y. This gives rise to another induced measure. Okay. Now, since we can talk of the unions and intersections of the elements from the sample space, we can talk of what are called as joint distributions. See, I will kind of hand wave now and not talk. I mean, not go to details of the definitions. So this is represented like this, which is a joint distribution of pair of random variables. Now this is evaluated at 2 points. No, x comma y, a comma b. Let's call it. Okay. What does this mean? We'll go to our own definition. This is the probability. Okay. So now this is like you take the X inverse of this particular event, the event that gets mapped to this particular thing under X. Okay, you take the Cartesian product of this under the random variable Y, take this event that gets maps under this inverse image, and that probability, right? So this will be the probability of some event A that belongs to F1 intersection some event B that belongs to F2. Is this clear? Oh, what happened to this? Is this clear? So we can talk of joint distributions, right? I mean, joint distributions are again, we are talking of probability of intersections of events. Now, these are intersections of events that are belonging to two different sample spaces. Now, these are, how do you get it? There you take first random variable, take its inverse image, get one event, take another random variable, take its inverse image, you get another event, take the intersection of those two, and that is and look at the probability of that, and that will give you the value of the joint distribution function evaluated at those two values. Okay, so similarly, you can also talk of conditional distributions. The definition of conditional distribution is slightly involved. Okay, let me not give you the definition of it. Okay, denoted by this. Okay, this is evaluated at one point. This is like x being equal to, or x, yeah, given y equal to some b. Okay, I mean, I don't want to in continuous random variables. No, this has a very this has an involved definition, but roughly you can see that as we are looking at the probabilities of these kinds of events, right? Conditional events. So we are looking, this corresponds to some conditional, the probability of some conditional distribution. It's the probability of some conditional event. Okay. That the definition of the conditional event is this, which is that you take the probability of intersection and divide it by the probability of the the uh, the conditioned event. So it has a similar definition, but yeah, you need a little bit of measure theory to know this, at least for the case of uh, continuous random variables. And by the way, all the definitions that I've given so far are for continuous random variables. If it's a discrete random variable, no, what happens is the mapping that the random variable does is element by element. So you are talking about the inverse images of singletons. Okay. This is conditional distribution. So basically, the 2 points that I wanted to drive home is that there can be vector valued random variables which would take the sample space and maps it to vectors, and there can be pairs of random variables where you should envisage, you should imagine two random experiments that are happening. Okay, so there is an association between those two random variables that happens through intersections and unions of events. Okay, and you can define joint distributions and conditional distributions. Now, definition wise, this is defined as the joint distribution divided by marginal of vertices. So it is defined mathematically, but yeah, so it always has a corresponding probabilistic interpretation as we were looking at. Okay. Okay. Questions? Aviroop?
Yeah, so I could not understand a couple of things. Can you scroll up a little bit?
In which part?
Yeah.
The vector value
Yeah,
random variable
no,
part?
after the vector value, when you are actually saying that, yeah, so A belongs to the event space F1 and B belongs to the event space F2. Then when we are talking about A union B, so the A and B, they belong to two different sets. So I cannot understand the notion how you can do a union. Yeah.
You can, no? See, it's like you take a set, let's say that we have two subsets of R. You can define a union of both of them, right? Why can't you do that?
Yeah, so that is because in that case the universal set is R. So my question is that
Same thing, I'm saying you're rolling two dice of different configuration. The universal set is same thing, right?
so in case of A,
that is why you remember I said toss a coin, roll a die.
yeah.
Then I erased that example precisely because of this. It will create confusions. In the example that I've given, the universal set is comprising of rolls of dice for both the cases, no?
Okay, so if we are considering one event space as rolling a die and another event space as tossing a coin, then the universal set is
then the universal set will be 1 to 6 and those two things, head and tail. That's all.
Oh, okay, so it is going to be F1 union F2?
Of course, sigma
yeah.
omega 1 cross omega 2. Sorry, this should be omega 1 cross omega 2. That would be your universal sample space.
Okay.
I didn't want to do that because of this precise reason. So if you roll a die and toss a coin, then how can you define unions is a question that I anticipated. That's why I said roll two dice.
Okay. And also, as the second question, when a little bit down, if you don't mind, a little bit scroll down. Yeah. So x inverse of minus infinity to a cross of y inverse of this one. So how are you replacing the cross sign with an intersection sign in the next line? I have a difficulty in understanding that.
See, the cross products here, right? In the Cartesian, this maps to one event, that maps to another event, right?
Okay.
So that is the intersection only.
Yeah.
Okay, so the point is right here when you talk of intersection, you talk of cross products of two sets, isn't it? This is cross product of two sets. So intersection is nothing but cross product of two sets, no?
Yeah.
That's it. Huh? Okay, Sarvesh.
Yes, it's the same thing. Like x inverse of minus infinity a gives a, correct? And
Gives
y,
A, that
yeah, and
that gives you
y
B.
that gives b, and same thing. Like it has a cross b, right?
Defined. It is defined that way. No, joint distribution is defined that way by definition.
Yeah, so it's a cross product, right? So
Correct. It is by definition.
yeah, so below it should be a cross b, right? So there will be pairs, ordered pairs of a and b.
No. A is no. So there are two sets. No, I'm talking about two sets here. So probability is defined. That is why you have the probability and intersections are defined. Okay. So here the joint distributions are defined that way. That if you evaluate it, they are actually the intersections of. In fact, I know where the confusion is coming from. Let's just say that these are intersections by definition. That's all. I think that will clear the thing, no?
Okay.
And that's the definition of joint distribution by the way. Yeah. Okay. Sanjay.
Sir, if we try to understand joint distributions with an example, so okay, let me just explain what I perceived by this statement is we want to find the joint distribution for events where there is a 3 on the first die and a 4 on the second die. Okay, so getting a 3 becomes event A, and on getting a 4 on dice 2 becomes event B. So we want to find
Those two gets mapped to different points by two different random variables. I look at the inverse image. That's all. Yeah, it's correct.
correct. So now when we want to find the probability that event A belongs to F1 and event B belongs to F2, so it will only
Both are
be
happening.
both are happening. So that means we will obtain the Cartesian product of F1 and F2, and in that only point 3 comma 4, where 3 is obtained on die 1 and 4 is obtained on die 2.
Agreed. That's the intersection that will happen. Yeah,
That is the
correct.
only intersection, right? Because
Correct.
otherwise, since
Correct.
both.
I
Okay.
I understand what you're saying. Yeah.
Okay, sir.
Yeah. Raghavendra?
Yes, sir. In this case, the X and Y have to be independent, right?
No, they need not be. If they are independent, then I mean, I've not defined independence, right? Random variables are called independent if the joint distribution happen to be the product of marginals. If they are independent, then intersection is null. They are not independent, right? This is the general definition. General
So there
definition. If they
can
are
be, so one
independent,
experiment
then
can be dependent on the other.
they are. They are actually. I mean, the moment I talk of joint distributions, they are dependent, no? If they are independent, then the joint distribution will become the product of marginals, isn't it?
No, what I meant is, say, for example, in this case of rolling 2 die, the outcome of the second experiment shouldn't depend on the outcome of the first.
I mean, the way we have conceived it, they are dependent. Independence is if P of xy is given by Px into Py, then it is independent.
Okay, but this is not a necessary condition.
No. Why?
Okay.
I mean, the way we have conceived the pair of random variables is that in general they are not independent, right?
Okay.
Hmm?
Yeah.
Okay. Shivam?
Yes, sir. I don't have any question. Just one thing that I am getting confused with small y, capital Y. So last time also.
No, where is small y? I'm not used small y. It's all
No,
capital
sir.
Y now.
Yeah, on the conditional distribution. Yeah. So it's all random variable, right? So capital
Yeah,
Y.
yeah. I'm sorry. My bad. Sorry. Yeah.
No, sir. In your previous lectures also, the small y and capital Y, we tend to use it here and there.
Interchangeable. Yeah. No. Yeah. Thanks for bringing that up. If I make that mistake again, just alert me. Okay. Ganta Murdo, so that I can correct myself. Yeah. See, yeah, this is, I think, what is how many times I've taught now? 2017 is when I started. This is 2024, 7 years. So on an average, I mean, not on an average, every time I've taught every semester, this is 14 times. And this online some 3, 4 times, but this 17, 18 times I've taught. So what you are seeing now is actually I've done gradient descent on my teaching based on feedback every time, and it has come to some optimum, and that is what you are seeing. So imagine what my students have the plight of my students 7 years back. I didn't know how to do board work, right? I was like, in spite of doing it for 15 times, 18 times, sometimes the notations gets here and there and all that. But yeah, I think I've improved, right? And a lot of my students tell me that I've like improved over time. That's why I have that feedback form, you see. Please use that. If you have any concern that you cannot, when Shivam was bold enough to tell me that I do this, I appreciate that. I don't mind. And you can tell me that this is like you're going fast, whatever. I don't mind. Okay, you can express it. But if you think that expressing that will embarrass you for whatever reason, uh, you have that anonymous feedback form. Uh, do put in your comments, right? Constructive, destructive. I told you, right? A lot of times students use it to vent out their frustration. It's okay at times you can do that, but don't use it for just venting out your frustration. Right? So that will be too much negativity. Okay. Great. Okay. So Shivam, thank you for that. If you notice such kind of a thing, just let me know. I'll try to be consistent as much as possible in notations. I understand how important it is to be consistent. Okay. Maybe I'll take this B out. I'll tell you why I wrote this in a while. Okay. So these are I'm kind of hand waving now because this is not a probability theory course, right? This is just to build some basics on it. Okay. Now, let us come to independence, conditional distributions, joint distributions, multiple random variables. Yeah, one other thing that is to be defined is what is called as a probability density function.
ఇందాక నేను దాని గురించి మాట్లాడలేదు కదా చెప్పాలి కదా బాబు
Was that some Gali in some language? If you speak in your language that I don't understand, right? What can I do? See, Galis make sense only if you make the other person understand what you are saying, no? So, see, I have again off topic, but this is a professional tip. I'm married for 10 years. So if I'm too angry, right, on my children or like on my wife, and I don't want to escalate the war, what I do is I'll start scolding them in Sanskrit or some other language that they don't understand. So that my anger is vented out, but they don't understand and respond back, so that no escalation happens. So, so maybe somebody is doing that way. Who knows? Okay. So probability density functions. So now probability density functions. Okay, notation wise, note that for distribution functions, I'm using the script P, right? I mean, two lines P. So for probability density functions, I use like small p. So this probability density function is a function, right? That is equal to the derivative of the distribution function, right? Evaluated at that point. That's all. Okay. Well, maybe not use A. Let's use some other thing here. Yeah, this is the definition of the probability density function. It's just
Sir,
the
one
derivative.
question.
Yes.
Sir, maybe I am moving ahead, but just for clarification, for continuous function random variables, we have CDF and PDF, like cumulative distribution and probability density functions, correct? And for
For
discrete,
discrete random variables, I'll tell you, so that will become probability mass functions. Distribution functions are the same. This will become probability mass functions.
okay, sir.
Okay, so good that you mentioned that. See, mostly in this course, we'll be dealing with continuous random variables. Yeah, good that you mentioned that probability mass functions. So this is for continuous random variable. Okay. For discrete random variable, the probability density function is nothing but the cost difference. Let's say distribution function evaluated at that and distribution function evaluated a plus 1 and a, no, yeah. That is the density function. This is for the discrete random variable. Okay. So please note that this this is not a probability. That is why, if you take an example, right? If you take a random variable, this notation is normally distributed with 0, 1. Okay. This means that the density function of this is equal to that thing 1 by 2 pi sigma squared e power minus x minus mu whole square divided by 2 sigma squared, right? I think there is a square root here. Yeah, I don't remember this, and I don't expect you to remember as well. This is for a scalar value case. For a vector value case, that is 1 by 2 pi to the power of d by 2, where d is the dimensionality, and you have the determinant of this matrix. So e power minus x minus mu transpose. So this is a vector of d dimensions. Sigma is a matrix d by d. This is x minus mu, right? This is what it is. So now note that this entire thing is a scalar, no? Time, this is d cross 1 times d cross d times, no, 1 cross d. So my x and mu are d cross 1. I'll tell you. Settle this for once for all. 1 cross d times d cross d times d cross 1. So this would be 1 cross d times d cross 1. This will be 1 cross 1 because x is in Rd. The range space of random variable is three-dimensional, which means that mu is also in Rd. Okay, this is the probability. Whenever we see in most of ML, right, we work with density functions. not distribution functions, because of ease of computation. That's all. When lot of standard metrics exist, lot of standard forms exist for density functions. Okay, what is density function? Density function is nothing but the derivative of the distribution function. So if you evaluate the density function at a point, right, what you are getting is the derivative of the distribution function at that point. That's all. Please note that if you evaluate the density function at a particular point A, you are not getting the probability of that point. Okay, so this is one take-home message. Evaluating the density function at a particular point will not give you the probability of that point. Okay, because probability of a point does not make sense. Probability, remember, is a measure that is defined on the elements of sample space always. Okay, evaluating the density function at a point will simply give you the derivative, the value of the derivative of the distribution function at that point. That's all. However, if you take the density function, right, and integrate it over a laying over a set, what do you get? This is equal to the distribution function evaluated at A. See, this is equal to the probability of that entire story. Do you understand this? What I'm saying is, evaluating the density function at a point, okay, is not equal to the probability, is not equal to probability of anything. Okay. However, integrating the density function over a set is equal to the probability. So for instance, right, if you take the density function and integrate it between A and B, what do you get? You will get the distribution function evaluated at B minus the distribution function evaluated at A. So this is a valid probability. You know this, right? So always remember that evaluating the distribution function will give you a valid probability. Evaluating the density function will not give you a valid probability, but integrating the density function over a range will give you a valid probability because that is equal to the distribution function. Is this clear to all of you? Okay. Okay, so now I think we have like enough background to any questions so far? Now let's come back to that problem of estimating genders from an image.
Sir, one question.
Before you ask the question, I have a request. With this background, right? Please go back to that the Goodfellow's book on machine learning and read the chapter on distribution and probability theory, please. Huh? So while you come to the next class, I expect all of you to know all this, because this actually kind of brings us to the end of the basic probability theory treatment. Okay, I don't intend to teach you probability theory because I assume that you people know it, but just to give this perspective, I spent some time. Please go back and brush up your probability theory fundamentals before you come to the next class. Huh? Please do that. Okay, questions.
Sir, when we have the probability density function and we have px of A, so there A, like it does not evaluate to minus infinity comma minus A, right?
Again, if you evaluate the probability density function at a point.
So it does not mean that it is a range from minus infinity comma A. It is strictly
No. It is simply it is simply means that you are taking the derivative of the distribution function and evaluating that at A. That's all.
Okay.
Evaluating see, if you suppose you plug in some value A into the Gaussian distribution and evaluate it, it only means that there is an underlying random variable, okay, with a distribution function. And that distribution function you take the derivative or the differential of that distribution function and evaluating that derivative at a. That's all it means.
Okay, sir.
Okay, but if you take the distribution function, if you take this Gaussian distribution, Gaussian density function, okay, integrate it within a range, then what you are doing is evaluating the distribution function at two different points, no? That is what I wrote. If you take it and take the running integral of this part, you get the distribution function evaluated at this point A. If you take the range, if you take the distribute density function and integrate it between a range, it is equivalent to evaluating distribution functions at those two endpoints and taking the difference, which is the probability. Because distribution function evaluated at a point will give you a probability.
Okay, sir.
Got it? So remember this, no? See,
And sir,
okay,
distribution.
let me tell you. So suppose there is a random variable that is uniform. Astik, I'll take your question. That is uniform between 0 and half. Okay. What is the density function of this? Do people know what the density function of this is? Uniform random variable between 0 and A and B. What is the density function of a uniform random variable between A and B?
2. 0 if less than 0. And half minus 0 is the
1
I
by
think it's the length.
b minus a.
1 by
1 by b minus a. 1 by b minus a. No. So it is equal to 0, right? If x is yeah, maybe it's easier to write it that way. It's equal to 2 if x is between this, right? And 0 otherwise. The density function of a uniform random variable looks like this, no? 0 and half. This is 0, this is half. The height is equal to 2. This is how the density function looks, right? All of you agree? Anyone has a question on this? Now, I mean, if we were to say that evaluating the density function at a point will give you a probability, how can that happen? It's contradictory, no? The probability is upper bounded by 1. Density function evaluated at a particular point here will not give you a probability. Do you see that? Do you appreciate that? This is an example that I have constructed to show you that evaluating the density function at a point will not give you a probability. Is this clear? However, if you integrate this and if you take a small area, this is a probability because that will evaluate something less than 1, between 0 and 1. Clear? Evaluating the density function at a point will not give you probability, but integrating that will give you probabilities. Is that okay? Because integrating the density function is equivalent to evaluating the distribution function at a particular point. Right? Okay. Astik?
Yeah, hi sir. So in the above integral where you are integrating it from a to b, I just have a doubt with the notation. So you have written px of small x and then d of capital X. Is it correct, or it should be d of small x? Okay.
Yeah.
And also
Mistake.
while you define the derivative, there also it should be small x, right? Where you
It
define the
depends.
probability.
It depends. I mean, this if it's a scalar valued random variable, then it's small x, right? If it's a vector valued random variable, what happens? It's the gradient that we define. That's all, right? Because you understand?
Mm-hmm. Yeah.
Yeah. Mhm.
Yeah. Yeah. Thank you. That's it.
Yeah. Okay. So if this is clear, so when does our class end? Is it at 12 or at 12:15? Like
It's at
officially.
12:15.
12:15, sir.
officially.
So can I continue for 10-15 more minutes? Okay. Because no, this actually is a nice time to stop. Yeah, no, we have topic wise, I'm saying we have come to the end of this. So let's come to machine learning. Okay, for now, let's do supervised machine learning. Okay. Okay, so what do we have? Suppose we have 1,000 images. Okay, with labels. This can be like, let's say these are gender labels. This can be any labels, so identity labels, anything. Okay. Now, this is what we have, this we understand. Now, everything that we do from now on has to be seen in the seen from the perspective of the distribution functions and random variables and all that. How do we see this? So let us represent this as a set D. Okay. I will introduce the labels afterwards. So this is x1, x2, x3, and x1000. Okay. Now each image, let's write it down here. Each image is what do you want, 2,200 into 300 dimensional. So how many? 660 to 60,000 pixels. Okay, this means that every xi is in R. Any confusion on this? Any question on this? Any question on this? This notation is clear. We have 1,000 images, all of them are in 60,000 dimension. How do we see that? So now from our language, right? Each xi is an element from the range space of a random variable x. You understand what's happening? So what is happening is the underlying random experiment, right? The random trial has been conducted 1,000 times. Okay. And there is an underlying random variable that has taken those outcomes and mapped it to some 60,000 dimensional space using this random variable. Is this clear? This implies that there exists an underlying probability measure and thus a distribution function. Do you agree? There exists an underlying probability measure and therefore a distribution function induced by x, correct? So that is represented as this, right? I mean, you say that this is a data that is sampled from this notation, this tilde says sampled from. Okay, what do you mean by sampled from? There is an underlying random trial that is happening, and there exists a random variable, and that random variable gives rise to some induced measure. These are elements from the range space of random variable. That is what this notation means being sampled from a distribution. This is how we write. You get the notation? So this is our starting point for machine learning. When we have data, we say that data has been sampled from a distribution. Okay, sampled from a distribution, not a distribution, because we have specified that sampled from T distribution Px. This is like data sampled from the distribution Px. Okay. What does that mean? That means that you understand the entire story, right? Now that there exists an underlying probability measure and there was a sample space, there is a random experiment happening, there is a random variable that mapped those outcomes to some real numbers, which is 60,000 dimensional real numbers. And what we see are the elements from the range space of it. And because there was a probability measure, there exists a distribution function. Yeah, that's what we have now. Is this clear? I just wanted to give you this worldview, right? I mean, had you knew this, then I would have not spent those 3 hours. So this is the worldview that I want you to have. Please ask me questions if you need clarifications at this point. Yeah, Indrajit?
Yeah, just trying to get, how did you get 60,000 on R dimensions?
See, every image, right? You have image is a 60,000 dimensional vector now, right? I mean, 200 pixels horizontally, 300 pixels vertically. So this is the one real number, second real number, third real number, fourth. I've just stacked them as columns and made it a long vector of 60,000 dimension.
Okay, I read that as 30C instead of 300. I didn't read 300. It was looking like 30C. Yeah, it's clear. Yes, sorry for confusion. Yeah, it's clear now.
Yeah. See, if it's BERT embedding, no, then it is some 712 dimensional vector. It doesn't matter. It depends on what your data is. Aviroop?
Yeah. So I have a question. So regarding you said that these x1, x2, x3, these are these belong to the range space of the random variable function, and there is a probability
By the way,
distribution.
I like your term, random variable function. That's what it is, okay? Yeah, but nobody calls it, unfortunately, a random variable function, but that's what it is. Yes, go on, please. Yeah.
Yeah. So the probability distribution function, which is induced by x, that probability distribution function and the probability distribution function of actually the outcomes, how are these two are related? I mean, are they equivalent?
No. Hold on again. No. What do you mean by probability distribution function of outcomes? That's not a well-defined term. Probability measures are defined on over outcomes, not distribution functions.
Yeah.
Are you asking how is the probability measure related to distribution function?
Yeah.
That's by definition. No, we have defined that here. That green thing. This is how they are related.
Yeah. Okay. Then my question
This is
is
how they
that.
are related, no? Yeah.
Yeah. Then my question is that how are these two probability measures they are related? I mean, how are they related?
There are no two probability measures. There is only one probability measure. There is a distribution function. Where are two probability measures here? There is only one probability measure, no? There is a
no, just somewhere in the top you mentioned, like, that we have outcomes and we have a set of events, and we have a random variable which maps them to certain real numbers, and we have a Borel sigma algebra and a probability measure. Yeah.
Not probability. It's not probability measure. It is an induced measure. Induced measure is called distribution function.
Okay.
The induced measure itself is called distribution function.
Okay. So
There
P1.
are no two measures. There is only one measure. Two measures will come into picture only if you have two random variables. If you have a single random variable, you only have one
Okay.
measure
Okay.
and one
Okay.
distribution function.
So I'm not even sure whether my question is correct or not. If it is wrong, then please correct me. Then how are P1 and Px they are related in this
Then
equation?
this is when you have two random variables. Okay. Are you talking about multiple
Not
random
this
variables
one.
or a single random variable?
Single random variable. The equations which you are just flashing. Right.
Which ones? This ones?
The place where you have written the induced thing, like the x over the arrow. You just went past it. Yeah, this one. Yeah.
Here. Where?
Not exactly. You just went past it. Okay, maybe I can just.
Here.
This one. Yeah. Omega 1 F1 P1.
Here there are two random variables, no?
Yeah, but on the left hand side you have written omega 1 F1 P1, and there is an arrow where x is a random variable, and this
Correct.
R real numbers. R means set of real numbers. B is the Borel-Siegel
Correct.
algebra, and Px. So
Is the induced measure under that random variable x? It is that is one distribution function. The induced measure itself is a distribution function.
Okay.
And another random variable induces another distribution function, and there is another underlying measure.
Okay. So
every
P1.
random variable has a measure.
Okay.
Measure P1 get induced to distribution function Px. Measure
Okay.
P2 gets induced to distribution function Py.
Okay. Got it.
Is that okay?
Okay. Yeah.
But here, right, when we are talking about data, there is only one measure that we are talking about, and there is only one distribution function.
Yeah.
Is that okay?
Yeah, it's okay.
Any other question on this?
Yeah, and sir, you are considering black and white picture because otherwise it will
No,
be
why?
multiplied. I recall they said.
No, every pixel is a real number, no?
Yeah, you are multiplying 200
No,
by.
what you are saying is there should be another 3-channel image here, not 200 plus 300 plus 3.
Yeah, right.
If it's 3, then you multiply this with 3, no? That's all. It is like 1,18,000 dimensional. That's all. Yeah.
Okay.
For now, I'm for the sake of ease, no, it doesn't matter. I mean, you should understand that the data dimension doesn't matter because it can be anything. It can be a picture, it can be some 30-dimensional speech vector, it can be some bird embedding. It doesn't matter what it is. Get it? This is only an example. So in general, right? In general, if I want to generalize this idea, I have to just say that all data is in some d-dimensional space. That's all.
Okay.
Right. So if it's an image, then it is 60,000 dimensional. If it's bird embedding, it's 7,000 dimensional or whatever. Got it? Yeah.
Yeah, thanks.
Okay. Any other questions? Okay. Now, suppose take another example, another scenario where suppose we have images, same thing, we have 1,000 images with labels. We'll take MNest itself, 60,000 examples with 50,000 examples. MNest has 50, training data has 50,000 examples in it. 10,000 images with labels. These labels are 10 labels, 0 to 9. 0 to 9. You have 10 labels. Okay. Now, how does the data represented? Data is represented like this. Every point is a tuple like this, x1, y1, x2, y2. You have x 50,000, y 50,000. Okay. Now, how do we use our worldview on this? Is that you say that this is sampled from an underlying joint distribution between two random variables x, y. Because x represents the random variable. So basically we are saying there are two sample spaces, right? There is X that takes the image space and maps it to 50,000. No, what is the dimensionality of image? Well, let's say that each image is in 784 dimensional because MNIST is a 28 by 28 image. Okay. So now this maps it to 784 dimensions. This is one random variable. There is another random variable. So yi is a discrete random variable that can take values. This is like rolling a die. Okay. Now there's another random variable y that takes another sample space omega 2 and maps it to a discrete set. And note that a random variable need not map in the range space of the random variable need not be continuous. No, it can be discrete as well. Now there are two random variables here, and the data is now modeled as coming from the cross products of these two, right? I mean, you take a picture and you associate, you sample one. I mean, you take a random trial from this sample space, you get a picture, and you make a random trial from this, and then you take a pair of them. That is your data point. And because there exists probabilities on the intersections and unions of these two sets, you can define joint distributions on it. Do you get it? Now, in this is supervised. This is typically called supervised machine learning. Okay, where you have two random variables and two sample spaces and two probability measures, basically, right? It is called supervised machine learning because you have one random variable corresponding to data. The other random variable is typically called as the label. Okay. Now the data has been sampled from joint distribution of X-Y. Is this clear? And whatever I defined here, now this is unsupervised machine learning where you have only one probability measure. In supervised machine learning, you will have two probability measures. One is called the data, the other measure for the labels. So this we will write maybe. This is a setting for unsupervised learning. This is a setting for supervised. So what changes? You see that we are sampling from PX here, right? There's one probability distribution function, and here we are sampling from the joint distribution of those two because there are two random variables. See, now we actually think about it. If you think about it, what was our problem? Our problem was that we don't know how pixels are related to these notion of digits, right? So the way we model it is that, okay, two random experiments are happening. One, somebody is writing that digit on like paper and being a picture is being taken and all that. Okay. There's one random variable that is basically converting all that into a real number. So once this is done, this is being now associated with one of these 9 digits, the notion of digits. That is another random experiment. So both of them have uncertainty, right? No, but you have joint distribution, which means that now every image, right, has a certain uncertainty or a probability of belonging to one of these 9 classes. Do you see that now? See, initially I said that this probability theory will give you a tool to handle uncertainty that incorporates uncertainty in construction itself. Now you see why. Okay. Now we don't talk about functions from y to x. See, in deterministic case, we were talking about functions that deterministically map elements of y to elements of x. Now we are not talking about it. We are talking about distributions. Okay, joint distributions between these two sets, which means that given every element in y, or rather every element in x, there is a certain probability associated with that belonging to one of these 9 classes. 9 labels. 9 elements from other set? Do you see that? I mean, I will concretize these ideas in next class. Okay, but I want you to appreciate, right? I mean, the whole branch of this probability theory was conceived because you start with a random experiment, right? and you have this notion of probability associated with events. Now you deal with everything, you model everything in terms of those random events and distribution functions, right? And you have that notion of uncertainty by construction. Is this clear? I'll continue from this in the next class. While I'll take questions. I'll continue from this in the next class. I'll concretize these ideas. But yeah, you should understand how to represent data. So data is represented as samples drawn from, this is actually called, samples drawn from a distribution. People also call this as data sampled from a distribution or samples data drawn from an underlying distribution. Okay, these are common words that are used. Whenever you see that they are drawn from a distribution, you should know the entire story. What's happening is that there is a random experiment. You get sample space, you get event spaces. There is a random variable that is mapping this to real numbers, and there is a probability measure assigned to the elements of sample space, or rather elements of event space, and therefore a distribution function gets induced, right? So when you say that the data is sampled from a distribution, this is what it means. Okay. Okay. Yeah, Prasanna. Prasanna Bhatt, go on.
Can you hear me, sir?
Yes, I can hear you.
Yeah. So in the last slide, I think you explained about x and y random variable function. So what is the relation between omega 1 and omega 2 here? That omega
yeah, there are two sets basically, right? I mean, there's no relation per se.
But whatever the.
But you can conceive, you can talk of intersections and unions between those two elements. That's all. Right? Those two are the two sample spaces. I mean, those two are sample spaces that would encompass the outcomes of these two random experiments. But these two random experiments are not independent, right? Quote unquote independent, in the sense that they are connected.
Yeah,
through
like only for the
distribution.
images that you have taken, like you will assign the number. So basically, like
No,
omega
you
1.
sample an image. Yeah, you sample an image. You sample a number. Associate them using unions and intersections.
Okay. Thank you.
Yeah, Raghavendra.
Sir, do we know this px or pxy in this case?
No, we don't. That's the whole problem in machine learning. The machine learning is, if I have to summarize machine learning in one sentence, it is this: given D, estimate px. That's all. That is machine learning. ChatGPT
So
also does that only. We will
we are
see
trying to
multiple
estimate
techniques to estimate px given D. Yes.
px or pxy? Or
depends, no? In unsupervised learning, you estimate px. In supervised machine learning, you estimate px. In fact, in supervised machine learning, you estimate py given x. I'll tell you next time. You estimate the condition
py
distribution given x.
given x. Okay.
Yeah, I'll tell you in the next class. That is actually the
okay,
probability
because
of gender given image.
okay, because these are sampled from those distributions, we say that they are kind of representative of the actual distribution.
No, they are actually sampled from the underlying distribution. No, they are completely sampled from the underlying distribution. Okay.
Okay. Okay.
But the one big problem with the statistics is, right? If when you are given samples from a distribution, how do you estimate the underlying distribution is the biggest problem in statistics. Giving samples from a distribution is not enough to estimate completely the underlying distribution. That is why it is machine learning is heavily dependent on the number of data points. The more the number of data points that we have from the distribution, the better our estimation will be. We will see all that in the next class. That is what I'll do in the next class.
Okay, that's because of either noise or maybe some things that we have not observed.
No. Don't call it noise or anything. Okay, there's something called law of large numbers. I will describe all that in the next class.
Okay, yeah, thank you, sir.
Yeah. So basically, take away from this class is that when you have data, you should start representing data, right, as samples from range space of elements from the range space of the random variable. And when we say that there is a distribution associated with it, you should know that it is the induced probability measure that is coming through the random variable. That is the biggest take home. Okay. Is it clear? Okay, let's stop here. But I have a couple of questions for you people. Let us maybe stop the recording. Yeah, people can leave, right?